Hello. In this video, we're going to be talking about the oxidation of alcohols. So if you have an alcohol, this is what we call a primary alcohol, so it's an alcohol bound to one carbon, or an alcohol bound to a carbon that's bound to another carbon. In this case, it's a secondary alcohol, so it's an alcohol that's bound to a carbon that's bound to two other carbons. You can oxidize these species. If you oxidize a primary alcohol, this ox or oxidize, you oxidize it to an aldehyde functional group. You can further oxidize aldehyde functional groups to acids or carboxylic acids. You can oxidize a secondary alcohol to a ketone. A tertiary alcohol does not oxidize. And let's look at why. On a primary alcohol, you have these carbon-hydrogen bonds that you notice are, each time you oxidize, they're going away. So you go from two carbon-hydrogen bonds in a primary alcohol to one carbon-hydrogen bond in an aldehyde, and then you're further oxidized to the carboxylic acid. There are no carbon-hydrogen bonds. For a secondary alcohol, you have one carbon-hydrogen bond, and now you have zero carbon-hydrogen bonds in that ketone functional group. In the case of a tertiary alcohol, you don't have any carbon-hydrogen bonds adjacent to that carbon-oxygen bond. So oxidation does not occur. Let's look at the general mechanisms. There are a number of different oxidants. There are lots of different oxidants, but they often go through this type of general organic mechanism where I'll have a very generic X, because this is, again, there's lots of different ways that this can happen, and we'll see an example later in this video. So the first thing that occurs is you somehow form an oxygen to X bond, and you wind up with this species like this, where you have an oxygen with X. A key feature of X is that it has to be a good leaving group. It has to be stable when it leaves the molecule. That is a key feature for all of these types of oxidants. You have these carbon-hydrogen bonds adjacent to the oxygen, the carbon-oxygen bond, and base will deprotonate the carbon-hydrogen bond. The electrons from that carbon-hydrogen bond will go to form a double bond between the carbon and the oxygen, and you'll break the oxygen leaving group, or oxygen X bond, to now form your carbonyl, in this case an aldehyde. Let's look at how that's occurring. So you have the electrons in the carbon-hydrogen sigma bond. So that's these electrons here with this arrow, and they're interacting with the oxygen leaving group sigma star. So because these electrons are being added into the sigma star bond, you are breaking that oxygen leaving group sigma bond. Again, when you add electrons to a sigma star, you break the bond. And so again, you're sharing electron density into this bond, which then breaks the bond. You'll see this is very, very similar to the E2 mechanism that you'll see in other videos, and you might hear from other classmates who are taking organic chemistry. So again, a very similar mechanism, E2. Now, how does an aldehyde get oxidized to a carboxylic acid? What happens is aldehydes, when they're in the presence of water, they can form what are called hydrates. So aldehydes get hydrated, that is, they react with water, and they form these types of species. And you can notice that now there's this carbon-hydrogen bond, there's an oxygen that looks a lot like an alcohol that undergoes the same mechanism as here, but then when you're done, you wind up with a carboxylic acid at the end. So if you are not doing your reaction in the presence of water, you're not going to have this oxidation all the way up to a carboxylic acid. Let's look at an example that you'll probably also see in lab. Bleach, like the bleach that you use for your clothing or for cleaning, can oxidize alcohols to ketones, and actually alcohols to aldehydes and acids. All these oxidations can work. Let's go for a secondary alcohol to a ketone as an example. So you treat bleach with a mild acid, in this case the sodium salt of sulfuric acid, and the solvent in this case is water. So it's a very environmentally easy to do and safe reaction. And so what happens first is that you have to do some steps to get it so that the bleach is ready to react with the oxygen atom here. And so what happens is you protonate the oxygen atom of bleach twice, and again, this acid is sufficient to protonate that twice, such that now water is a good leaving group, and that oxygen-chlorine bond is quite weak. That you'll have your alcohol act as a nucleophile and form an oxygen to chlorine bond and give you now a protonated form of what you've seen before, where you have this chlorine atom as your leaving group. You will deprotonate this to get now the neutral molecule, which is set up to, it might not look like what you've seen on the previous slide, but I will color code it so it looks a lot like it. You have this hydrogen atom that's been there the whole time, implied in the drawing but not drawn in, but it's been there the whole time. And you have this oxygen-chlorine bond where chloride, Cl-, is a really good leaving group. One way of knowing that chloride's a good leaving group is that HCl is a strong acid, so therefore chloride is very easy to dissociate from molecules. So water will act as the base here. It doesn't have to be a very strong base because this is a very weak bond. And you will form your ketone. You will also have chloride as another, just to conserve and keep track of all of our atoms. You have chloride and a little bit of the acid coming off as well. So you'll note that the acid needs to be used in excess in this case because there are several steps where you're protonating the molecules and it's not catalytic. As a little bit of bonus material, so you're not going to be required to look at this bonus material in an exam or in a quiz, but I find it very fascinating that nature has a different way of oxidizing molecules. Nature will take, for example, if you were to drink ethanol, nature has an enzyme called alcohol dehydrogenase. So it dehydrogenates, it removes hydrogen, the hydrogen here and the hydrogen here, that's implied. It removes hydrogen, effectively hydrogen gas, from your alcohol to give you an aldehyde. And it uses a molecule called NAD+. This is a cofactor of the enzyme. This is the nicotinamide portion of the NAD+. This is kind of the business end of the molecule. So one thing that you'll note that nature does is it does something that it's very different than the mechanism you see organic chemists use. The base will deprotonate the oxygen atom, and this carbon-hydrogen bond will get transferred over to the NAD+, and it will form what's called NADH. This is what's called a hydride transfer, so it's H- is effectively being transferred over to the NAD+. This only occurs because it's happening in an enzyme. So this is not a way we normally, as organic chemists, like to draw our mechanisms. It's not only how we don't like to draw them because having a hydride being kicked off in solution is a very high energy species. This only works because this is in the context of an enzyme. That's why it's bonus material as opposed to normal material. I'll highlight that there was this implied hydrogen atom that's been here all along. Another thing I want to point out is that when you have this acetaldehyde, this gets further oxidized to the carboxylic acid using another enzyme that's called aldehyde dehydrogenase. So there's alcohol dehydrogenase and aldehyde dehydrogenase to give you a carboxylic acid. And this is how your body deals with the poison of having an alcohol in your system. This is also, it's at this stage, is what can give you a hangover, and it makes you feel crummy because you are, because aldehydes can be pretty unsavory in your body. Aldehydes are quite reactive, as we've seen in other slides. Again, the thing I really want to emphasize about this mechanism is that this type of hydride transfer is not common in organic mechanisms, and it's found where these enzymes are key. NAD+ doesn't just simply go around oxidizing all the alcohols in our body. That is, it doesn't react with all the sugars and all the alcohols in our body. It needs the enzyme present. So keep that in mind. Don't have hydrides being transferred in your organic chemistry mechanisms, at least not for this class. All right, thank you for your time, and I look forward to your questions.